Yes. Yes. F is a flux. Yes. It's another flux term. Yes. Okay. Okay, good. So you're thinking about units here. So are you physics major? Okay, good. Uh, you're thinking of units here. So W has a unit of the conserved quantity, right? W doesn't have to be speed. W is the conserved quantity. F is the flux of the conserved quantity. It usually has the units of speed times the unit of the conserved quantity, right? It's the flux of the conserved quantity. So it's kind of the uh, F is the amount of conserved quantity going through a unit area in a unit amount of time, right? So it's if you take the unit area and the unit amount of time into consideration, and if you think of the W itself as the conserved stuff per unit volume, you can see F is equal to the unit of the conserved quantity times a speed. Yeah. 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 D has the same unit as U. Exactly. Exactly. Yeah, this case we have a linear relationship between W and U. If you have a nonlinear relationship, you should be looking at the derivative, right? So for example, if you say W has unit of X, okay, then so it's basically let's say X per meter cube, all right, okay, and so F has unit of the amount of X going through a unit uh area per unit time, right? So basically partial F partial W would have a unit of meter per, I mean it's a unit time in second, so it has a unit of meter per second, so it's kind of a speed type of unit. So D would also have a, because D is like the eigenvalues of partial F partial W, it has the same unit as partial F partial W. So D multiplied by W has the same unit as F. Right. Good to double check a lot of things. You can usually find bugs by thinking of units. So that's a good way to find bugs. Any other questions? Yeah. Yeah. This viscosity go to zero. Okay. Good question. The question is, how do we handle physical viscosity? We have not talked about how to handle physical viscosity yet. But if you do have physical viscosity, the way to handle it here, I think it's good for me to discuss here, would be you would have two terms, right? You would have F that is a function of W. My total flux is F as a function of W plus some viscosity mu times it's usually minus here, minus times partial W partial X. Oops. And when you discretize here, the F, the total F would be equal to the flux you would apply to the inviscous problem minus a mu times delta X over Wi plus 1 minus Wi, right? That's like a finite difference approximation of the first order derivative at the interface, right? This is a second order approximation of partial W partial I at xi plus half. So the derivative term you approximate with finite difference, and then I'm not saying you use finite difference to approximate the whole viscous term, because the whole viscous term is the derivative of the F. I'm saying using finite difference to approximate the first order derivative that lives within the flux. Okay, that gives you a conservative scheme. It still conserves the quantity numerically, but the first order derivative is approximated using finite difference. Does that make sense? Any other questions?